Okay, so let's uh, let's solve one of these water mixing problems. All right. So here we go. Geez, I can't even get this thing to work here. Here we go. Putting hot metal in water. Okay, this same exact method will work for, say, if we were mixing an amount of cool water with an amount of warm water and trying to find the final temperature. But in this case, we're going to use a piece of hot metal. We'll say it's iron. Okay, so we have an iron cube, say. And I guess you could kind of consider this a calorimetry problem in a way. Okay, and we have a cup of water here. So inside our cup, there's some amount of water. Okay, and let's put some values on things here. Let's make this 40 grams of iron, and we'll give you the C, which is the specific heat of iron at 0.45 joules per gram per degree Kelvin. Okay, we'll talk about what's going on here because we're going to be dealing in Celsius and why that's okay. And we'll say that this is at 250 degrees C. We'll say the water's at 20 degrees C, and we'll say that there's 250 grams of water. Okay, and the famous C of water, 4.18 joules per gram per Kelvin. Okay, remember if we were dealing in calories, this value would be 1, but we're not. All right, so now the question is, if I place this hot iron into the water, what final temperature will we have? We're going to make a couple of assumptions as well. In real life, well, this cube is over the boiling point of water, so the instant it touches a small bit of the surface, there will be some steam released, right? That little area of water would be instant or nearly instantly brought to a boil. So we're going to make that assumption that no water actually boils. Okay, so no water boils. And the other thing is that all energy stays in the system. So we're not going to account for, energy that might flow out to the air and so on. Okay, does that make sense? All right, so basically what will happen is, according to the way that thermodynamics works, the metal cube will cool. All right, and the water will heat up. Okay, doesn't work the other way. And so what that means is, our designation for heat in thermodynamics is Q. So the Q lost by the iron will be exactly the same as the Q, or energy, gained by the water. All right, so the Q of the system is set. Does that make sense? All right. And I guess the proper way to probably write this is that the Q lost by the iron, which will be a negative value, is equal to Q gained by the water, which will be a positive value. So in order to make that equal, you got to fire in a little negative sign here, okay? To just make that correct and hopefully have our signs work out at the end. So we just had a discussion as to where we put the negative sign. Doesn't matter. You can put them on either side, and really the reasoning for that is just, if we don't put a negative sign in, and one of these values comes out to be a negative, which it will, right? The iron is losing, so when we get to the temperature change, what you have is you have the final temperature minus the initial temperature. Well, the final temperature is going to be lower, so that's going to end up being a negative value. If we don't put a negative in, it's kind of like we're saying this: 1 equals -1. That doesn't really work. What we can do is we can slap a -1 on there. This is correct. Or put a negative here. This is now correct because we're saying a -1, which is 1. So it shouldn't matter where we put the negative, which side we put it on. We just need to put it in there somewhere. Okay, so now Q equals Q, and we know from before that in a heat problem, Q equals MC times the change in temperature. So let's do iron first. We've got the mass of the iron times the specific heat of the iron times the delta T of the iron. Okay? And on this side, yeah, we'll just leave this color. Now this delta T and this delta T are not equal. Okay? They're not equal. But what will be equal is the final temperature. Okay? Heat will flow out of the iron and into the water until there is no more gradient between them, no more difference between them, and then heat will stop flowing. Okay? It will come to an equal temperature at that time. We need the heat gradient to have a flow of heat from one place to another. Or I should say temperature gradient, right? Not heat gradient necessarily, but a temperature gradient. So we'll flow from the hot to the cold. And then we have to look at this separately. So delta T here is the final temperature, which is what we're looking for, which will be the same between these two substances, and subtract the initial temperature, which is 250 degrees C. Now, if we look, my C value is in terms of kelvins, but you have to remember that a Kelvin and a degree Celsius are the same size. The degree Kelvin, I shouldn't say degree Kelvin, the Kelvin and the degree Celsius are the same size. And seeing as how we're dealing with a change in, okay, it's fine to just leave it in terms of Celsius. You don't have to convert it to kelvins. If you did convert it to kelvins, it would still work. You would just get an answer in Kelvin rather than degrees Celsius, okay? So in other words, using the absolute temperature here is not necessary because we're dealing in a change in, and the size of the units is the same. There's different places on the scale, okay? Hopefully that makes sense to you. Okay, and we still need this and this. Okay, and then for water, similar but different. We've got to make sure we bring that negative sign along. So now we've got TF, which will be the same at the end, and that is minus 20 degrees Celsius. Okay, so let's do the distribution here of our numbers. Distribute them in. So here we get, so we're going to do this, right? Distribute it in. Get that. No worry, we'll get to numbers in a second here. Okay. And we'll remember to bring the negative along for the ride. Okay, so let's, I think probably at this point we might as well put numbers in. After we'll come back and maybe try to find a general formula. But at this point, let's do some numbers, okay? So here we've got 40 grams, right, of iron, and we've got 0.45 joules per gram Kelvin. And really I could substitute C in for that, which probably would make more sense the way I've got it written, but we'll just leave it like that for now. And that's times TF minus the same here. Okay. I'm just going to continue it down here since I'm sort of out of room. Okay, mass of water, 250 grams. Oops. Oh, for goodness sake. Okay, sorry. We'll get there. Okay. Plus. All right, so If we do this, we're going to cancel there and there. Okay. Over here, we'll cancel grams and technically temperatures, right? Same thing. Here, and here, and here, and here, and here. And let's crunch some numbers. Okay, so this works out to be 18. And this is 4,500. So we should get, let's see here, 18 joules per Kelvin times TF minus 4,500 joules equals, so this one works out to be 1045 plus that. Right. Just these units are the same. Okay. Okay, so now we'll add the 4,500 to the other side and add 1045 to this side. So what we should end up with then is we should end up with 18 plus that equals 25,400 on this side. All right, and then add these two together. So 1045 plus 18. Okay. And TF equals. Now remember, actually technically, although I'm using Kelvin, really it's degrees Celsius. That might be a little confusing, but you should get 23.9. And although it says Kelvin, it's actually in degrees Celsius. We were working in degrees Celsius the whole time, and we should have just written our C's in terms of that. Would have made more sense, but there we go. All right, so someone asked if we could find a general formula from this, and yeah, we should be able to. So why don't we work, just take a second and see if we can solve for a general formula. Not that I want you to memorize a general formula. It makes way more sense to understand this, okay? Just because we're physics students and for whatever reason we like to do this kind of thing, see if we can work out a general formula. So let's just go back to where we were. We've got, what do you want to call the object that cools down? I don't know, like H, the hot object, for our general formula, and C, cool object? Why not, right? No, hot. Okay, and then TF minus TI equals negative M of the cool object, C of the cool object, TF. And I guess we gotta call this TI hot. Call this TI cool. All right, so do our distribution. So we should have M hot. Oops, that's a B. M hot, C hot, final temperature, okay, minus M hot, C hot, TI hot. I don't know. Okay, and then we've got subtract M C C C T F plus M C C C T I C. All right, so there's your general formula. Or do you want to arrange it differently? It's a little ugly, so let's see if we can get it a little bit prettier. So I'm going to add this to both sides. I'm going to add this to both sides. So let's see what we get. So we should get then M H C H T F plus M C C C T F equals M C C C T I C plus M H C H T I H. And can we go any further at this point? We should be able to pull TF out of here, I believe, right? So you should be able to go to this now. TF times MHCH plus MCCC, right? So we distributed it out. Equals, and do you want to do the same on this side? No, you can't, because they're not the same. Sorry. So MCCCTIC plus MHCHTIH. And our last step will be to divide this off. I know you guys hate algebra, but it can be your friend at times. It's not like I would consider this overly difficult, really, algebra-wise, but yeah, well, for sure. So, if you were space monkeying the problem, you might be like, just give me the formula. If you really understand it, okay, you should be able to work from this premise here, right? If you start with this premise, it's going to all work out, and you can't go wrong. Exactly. If you work from a point of understanding the problem, which is always the goal, you'll be able to solve it. If you're just like, where's that formula I used to solve this? Well, you're never really going to understand what this is or where it came from, but, you know, what can I tell you? All right, so that wraps that up.